we looked at what actually constitutes the study of blood, I mean hematology, and we're able to establish the scope of the study of hematology. And we established that the study of hematology actually encompasses the components of blood, the physiology of blood, that is talking about the functions of the blood. We also looked at the disorders and diseases that are associated with blood. Then we look at blood as a medicine where blood products could be used or given to an individual whose blood level is low or the individual is lacking a particular component of blood, and that falls under blood transfusion therapy. Then we also looked at the size where blood cells are being produced, I mean the blood forming tissues and organs. In today's lesson, we want to look at the production or the formation of blood in these blood forming tissues or organs. We want to start by introducing a terminology which refers to the production of blood, a terminology which refers to the production, a terminology which refers to the production or formation of blood. Formation of blood. In the language of medicine, the word part for production or formation is poiesis. So all medical words that ends with the word part, poiesis, means production. And in the same language of medicine, the production or formation of blood is a definition of the term of a particular medical term, and we want to establish the medical term now. So we have production or formation. So we say that in the language of medicine, production is called poiesis and blood is called hemat. So blood is called hemat or heme. So hemat is a Greek translation which means blood. So either hemat or heme, both means or refers to blood. Now, the definition of all medical words actually begins from the ending part of the word, that is the surface of the word. And so if we are having production or formation of the blood, it means that this definition actually started from the ending part of the word. So it means it started from the suffix. So, and the latter becomes the beginning part of the word. So the production of what? Or formation of blood, if you want to construct the medical term for it, then that will begin with the word part, hemat. So it will begin with the word part, hemat, plus poiesis. So we will create the medical word. Because poiesis begins with the letter P, and in the formulation of medical words, the rule is that when joining two words pass together, a suffix to a root word, and the suffix begins with a consonant, we need to put a vowel between the suffix and the root word. And so therefore, we put the vowel O, because the vowel O is the most commonest vowel. So we put the vowel O here and we form the term hematopoiesis. So hemat meaning blood, poiesis means production. The letter O is just a vowel to connect these two words pass together and to also enhance the pronunciation of the word. So we have the term hematopoiesis. So assuming that we went by the other word part for blood, we will create the word, so that will have been heme plus poiesis, and that will yield hemopoiesis. Hemopoiesis, when we introduce the vowel O. So the term hematopoiesis and hemopoiesis mean the same thing. In other words, we can use hematopoiesis and hemopoiesis interchangeably. So hematopoiesis or hemopoiesis both refers to the production of blood. The production of blood. So this is the terminology we'll be using along the line when it comes to the production of blood in the blood forming tissues or organs. So the various size or the blood forming tissues or organs, or the process of blood cell production, in other words hematopoiesis, could be appreciated from this level. We understand that when the male sex cell and the female sex cell unites or they fuses, we form, so the male sex cell actually refers to the sperm cell from the male meeting with the egg of the female, we form a zygote. So we form a zygote. So when the male sex cell or the male gametes fuses with the female gametes or the female sex cell, that is the egg, we form the zygote. So this zygote actually is the first cell that is being formed from the union between the sperm cell and then the egg. From this zygote, that what makes up the whole organism is found. This zygote contains cells that will give birth to all the cells of our body. And because the zygote contains cells that can give rise to all the other cells that makes up an organism, the zygote is said to contain stem cells, or the cells that make up the zygote are considered as stem cells. So the zygote is made up of what? Stem cells. Now, stem cells have potentials or potencies. So it is important we establish the potency or the potential of the zygote. Now, we are saying that the zygote, the stem cells in the zygote will give birth to all the other cells. So all means total. So all means total. So that means that the zygote is having a total potential of all the cells of our body. And for that matter, the zygote is considered as a totipotent. So tot comes from the word total, and potent coming from the word potential. The I is the vowel used to connect the tot and potent together. So we have the term totipotent stem cells. So the zygote, once the male sex cell and the female sex cell, I mean the sperm cell and the egg, unites to form a zygote, we form a totipotent what stem cells, or the zygote contains totipotent what stem cells. Now, blood cell production does not happen in the zygote state. So the totipotent stem cell, in other words, is a stem cell that can give rise, all the cells of the body can give rise to all cells of the body, including the placenta and embryo, or the umbilical cord. The placenta and embryo. So this is a totipotent stem cell. Remember that the developmental stage will not remain in the zygote state. As a matter of fact, the zygote will undergo further cell divisions and development. The zygote will undergo series of divisions through the process of mitosis, to series of divisions, to form the embryo. So the zygote undergoes further cell divisions or undergoes divisions to form what is called the embryo. So we move from the zygote stage. So from the zygote stage, we are moving from a totipotent stem cell to the embryonic stage within the embryo. So in the zygote stage, there is no production of blood cells in the zygote. So, and when we get to the embryonic stage, so within the embryo, this is where blood cell production begins. Just as there are stem cells in the zygote, there are also stem cells in the embryo. And the stem cells of the embryo is limited when it comes to potential as compared to the zygote. Remember that the zygote is a totipotent stem cell that can give rise to all the cells of our body, including the placenta, the umbilical cord. But the embryo is not totipotent. The embryo rather is a pluripotent, or the embryo contains pluripotent stem cells. So pluripotent stem cells, implying that pluri means many. So pluripotent stem cells are stem cells that have many potentials, but they are limited when it comes to the production of the placenta and then the embryo, so the umbilical cord. So pluripotent stem cells are the stem cells that are found in the embryo. Within the walls of the embryo, within the walls, within the embryo, within the embryo is a sac called the yolk sac. Inside this sac is where the stem cells that are responsible for the production of blood cells are located. Now, stem cells that are responsible for the production of blood cells are called, stem cells responsible for the production of blood cells are called hematopoietic stem cells. So stem cells that are committed to the production of blood, they are described as hematopoietic stem cells. So within the yolk sac are the hematopoietic stem cells that will give rise or give birth to the blood cells that we see in circulation. Now, the walls of the yolk sac, is where we find these hematopoietic stem cells. So the walls of the yolk sac contain the hematopoietic stem cells. And technically, the production of blood or hematopoiesis in the embryonic stage actually happens within the first 2 months. Within the first 2 months. The first 2 months of gestation. The first 2 months of gestation or pregnancy. Gestations also means pregnancy. Within the first 2 months of gestation or pregnancy. So first 2 months of gestation or pregnancy, that is where the yolk sac begins the production of what? Blood. Now, the yolk sac, when we take the embryo basically has 3 layers, namely the ectoderm. The embryo has 3 layers, which include the ectoderm. 3 layers makes up the embryo. So ectoderm, ecto means outside. Then we have the mesoderm. Meso means middle, mesoderm. And then we have the inside layer, endoderm. Endo means inside. Meso means middle. Now, this yolk sac, where the blood cells are being produced from, is actually a part of the middle layer of the embryo, that is the mesoderm. For this reason, the production or the yolk hematopoiesis, production of blood in the yolk sac, which is called the yolk sac hematopoiesis. The yolk sac hematopoiesis is also called mesoblastic hematopoiesis, so named after the middle layer of the embryo. So we have the first phase of hematopoiesis, which occurs in the first 2 months of the fetal life, and what we have there is the yolk sac hematopoiesis or hemopoiesis. And because this is occurring in the mesoderm, that is the middle layer of the embryo, it is so named after this layer called mesoblastic hemopoiesis. Then in the second phase of gestation, that is from after the 2 months onwards. So this 2 months technically is 8 weeks. So after the 8th week, so from the 3rd month onwards, so from the 3rd to the 5th month onwards, from the 3rd to the 5th month, the embryo undergoes further development. So it doesn't stay in the embryonic stage forever. So there is going to be certainly some development. So when development occurs, the embryo is transformed to what is called the fetus. So we have the zygote stage, we have the embryonic stage, we have the fetal stage or the fetal stage. From the 3rd to the 5th month, which constitute or which makes up the fetal stage. So which is the fetal stage? What actually happens is that in the fetal stage, organs such as the liver, so the liver is the first blood forming organ to appear in the fetal stage, that is from the 3rd to the 5th month onward. The liver comes first and later on the spleen comes in. So the liver and the spleen begins the production of what? Blood. This implies that stem cells move into the liver and seed the liver. Stem cells migrate into the liver and then the spleen. But it is the liver that comes in first, and much of the blood at this particular stage will be coming from the liver. And because majority of the blood is coming from the liver, this stage of hematopoiesis is so named after the liver as hepatic hemopoiesis. Hepatic hemopoiesis. Hemopoiesis. So there is blood cell production occurring in the liver, and there's blood cell production occurring in the spleen. But the liver contributes to much of the blood cell production, and it is so named after the liver as hepatic hemopoiesis. So we have mesoblastic hemopoiesis, so named after the middle layer of the embryo. And then the next stage is that the embryo will undergo further development to form what is called fetus, and that makes up the fetal stage. So the fetal hematopoiesis at the fetal stage, in fact, the liver is the first organ to appear, and later the spleen comes in. So we have the fetal hematopoiesis, specifically hepatic hemopoiesis, so named after the liver. Then we move on to the third phase. So we are moving away from the 5th month to the 6th month and 7th month onwards. So we are in the 6th month of gestation, or the 6th month of pregnancy. So from the 6th month onwards, meaning from the 6th, 7th, 8th, and 9th month, the fetus begins to form bones. So bones begins to develop. And these bones that are developing contains a red matter. And that red matter found in the bones is called the red bone marrow. So we have red bone marrow found in the bones. So we have red bone marrow. And what actually makes the bone red is as a result of the migration or the seeding of the bone marrow with hematopoietic stem cells. So hematopoietic stem cells, on an appearance, they look red. So from the 6th month onwards, bones begins to form, and these bones contain a marrow, and this marrow is called a red bone marrow, which is found at the entire length of the bones. So from the 6th month onwards, we have the bones coming in, and blood cell production in the bone marrow is called myeloid hemopoiesis. Myeloid means bone. So we have myeloid hemopoiesis. So basically we have 3 types of hematopoiesis when it comes to the developmental stages. We have the yolk sac hematopoiesis, also known as the mesoblastic hemopoiesis. We have the hepatic hemopoiesis. We have the myeloid hemopoiesis, which technically implies hematopoiesis occurring in the bone. At this stage, from the 6th month onwards, where blood cell production is occurring in the bones, it isn't that the liver and the spleen have stopped the production of blood cells. Production of blood cells still occurs in the liver and then the spleen, but much of the blood is coming from the bones at this point in time. Now, once we get to the 9th month or the 9th period of gestation, so at the 9th month of gestation, of the 9th month of pregnancy, when the baby is being given birth to, when now the child now comes out of the mother's womb, this is now called a neonate or newborn. So notice the names that are given to the developmental stages in gestation. So we have the male and then the female gametes coming together will form what we call the zygote. Then the zygote undergoes further cell divisions through the process of mitosis to form what is called the embryo. Then the embryo undergoes further development to form what is called the fetus. Then it is the fetus that will undergo further. The fetus, once the fetus is the last stage in the womb. Then when the fetus come out from what? The womb, or come out of what? The woman, then the fetus, now the new name is called neonate. Neo means new, nat means birth, so new birth or newborn. So that is the names given to the various developmental stages. So we just look at the embryonic hematopoiesis, or the yolk sac hematopoiesis, or the mesoblastic hematopoiesis. It is important we note the various types of hemoglobin molecules that are produced in each of these stages of hematopoiesis. So when we take the yolk sac hematopoiesis, the yolk sac hemopoiesis, the hemoglobin molecules that are produced in the yolk sac hemopoiesis, they are called embryonic hemoglobins, because the yolk sac is found in the embryo. So embryonic hemoglobin. So we have the embryonic hemoglobins, and these embryonic hemoglobins are actually under the influence of genes. So there are certain genes that code for the production of these embryonic hemoglobins, and these genes are located in chromosome 16 and chromosome 11. So we want to look at briefly the embryonic hemoglobins that are being produced during the yolk sac hemopoiesis or mesoblastic hemopoiesis. So we have these globin genes. So in general, there are 6 structural globin genes. There are 6. So in general, there are 6 structural globin genes. There are 6 structural globin genes, and each of these 6 structural globin genes will give rise to a globin chain. So in total, these 6 structural globin genes will give rise to 6 globin chains. Each gene will give rise to 1 globin chain. So if we have 6 structural globin genes, then we'll have a total of 6 globin chains. Now let's look at these 6 globin genes and their locations in the chromosome. So when we look at these 6, we have the zeta globin gene and the alpha globin gene. So the zeta and then the alpha globin gene, they are located on the short arm. They are located on the short arm of chromosome 16. Chromosome 16. So the zeta and the alpha globin genes are located on the short arm of chromosome 16. So these are just 2 of the globin genes. So the remaining 4 genes, remember that there are 6 structural globin genes. So the remaining 4 globin genes will be located on the chromosome 11. So the epsilon, the gamma, the delta, and beta globin genes are located are located on the short arm of chromosome 11. So this is just a few, just a simple genetics. So we are looking at the yolk sac hematopoiesis, and we say we want to appreciate the hemoglobin molecules that are produced in this yolk sac hematopoiesis, and we said the yolk sac is actually found in the embryo, and therefore hemoglobins that are produced in the embryonic stage are called embryonic hemoglobins. And we said that in general there are 6 structural genes, and each of these 6 structural genes will code for a globin chain. And so at the end of the day we will have 6 globin what chains. And these genes, these 6 genes are actually located on 2 chromosomes. Remember that genes are located on chromosomes. And so we have 2 chromosomes here. We have chromosome 16 and we have chromosome 11. The zeta and the alpha globin genes, they are located on the chromosome 16, whilst the epsilon, gamma, delta, beta globin genes, they are located on the chromosome 11. So chromosome 11, that is where we'll find it. So when we pick, so remember in chromosome 16, we have the zeta and then the alpha. Then chromosome then we have in chromosome 11 we have epsilon, we have gamma, we have the delta, and then we have the beta. So epsilon, gamma, delta, beta, 4 plus 2, that makes 6. And as the developmental stages occurs, we construct the hemoglobin. So the construction of the hemoglobin molecules is by the combination of the chain coming from the chromosome 16 and the chromosome 11. So we combine, so the zeta and the alpha globin genes on chromosome 11, they give rise to globin chains. We call them the alpha-like globin chains. So those coming from chromosome 16, they are called alpha-like globin chains, whilst the globin chains are rising from genes in chromosome 11, they are called beta-like globins. So we have beta-like globins. So we have the alpha-like globins actually refers to the globin chains arising from the zeta and then the alpha globin gene located on the chromosome 16. And the beta-like globin chains are the chains that originated from the epsilon, gamma, delta, and beta globin genes, which are located on chromosome 11. And so to construct the hemoglobins that makes up the embryonic hemoglobin, it is the combination of the alpha-like globin chains from the chromosome 16 and the beta-like globin chains from chromosome 11. So if we combine, so let's look at the first hemoglobin. So if we combine the zeta, and remember that in constructing, hemoglobin is a tetramer. So it is a combination of 2 chains of the alpha-like globulins and 2 chains of the beta-like globulins. So if I pick zeta, so this hemoglobin is going to be 2 zeta chains. So you pick 2 here and pick 2 there. So 2 zeta chains. Then I pick epsilon. So 2 epsilon chains. This will give me the first embryonic hemoglobin, which is called hemoglobin GOA1. So hemoglobin GOA1. Then I can also pick up alpha and combining with the same epsilon. So we have 2 alpha chains combined with 2 epsilon chain, and this will give me hemoglobin GOA 2. Hemoglobin GOA 2. So we take the zeta combined with epsilon, 2 zeta chains, 2 epsilon chain. That gives me hemoglobin GOA 1. Then I pick the alpha chain from the chromosome 16 combined with the same epsilon. So 2 alpha, 2 epsilon will give you hemoglobin GOA 2. Then the third one is the combination of, we take the zeta chain, so 2 zeta chain, then we combine with the gamma, so 2 zeta chain as against 2 gamma globin chains. Then we form hemoglobin Portland 1. Hemoglobin Portland 1. So basically these are the 3 major hemoglobin molecules that are found in the embryonic stage, or the embryonic red blood cells contain these hemoglobin molecules. So now let's look at the fetal stage. Remember that once we move from the embryonic stage, we are moving towards the fetal stage. It is the fetal stage that is where the liver has come into play, and the liver now begins the production of blood cells. So what happens in the fetal stage is that, so let's put here, so the fetal stage, or the fetal hematopoiesis, the fetal stage, so the fetal or the hepatic hemopoiesis, fetal or hepatic hemopoiesis. What happens is that if you want to know the class of hemoglobins that are produced in the fetal or the hepatic stage of hemopoiesis, there is going to be a class switching. There is a switch of the zeta globin chain. There will be a switch of the zeta globin chains to the alpha. So the zeta globin genes, or the chains, will switch to the alpha. And then we will have the epsilon switching to gamma. So there is going to be a switch of the zeta globin chains to the alpha, and then the epsilon globin chains will be switched to gamma. This implies that if we take hemoglobin GOA 1 and the zeta is switching to, so if zeta is switching to alpha, then it implies that we will get 2 alpha chains here, because we are in the fetal stage, and these hemoglobin will undergo transformation. So it means that 2 zeta chains will now become 2 alpha chains. Epsilon will switch to gamma, so we'll get 2 gamma chains. And this is called hemoglobin F. F stands for fetal. In the same vein, we have 2 alpha chains here, 2 epsilon chains here. The alpha will still remain the alpha because there is no switching of the alpha. The epsilon will be converted to gamma, and this will also be hemoglobin F. So we now have 2 alpha chains. Epsilon will switch to gamma, and we'll get 2 alpha chains and 2 gamma chains, so hemoglobin F. The zeta here, the zeta will switch to alpha, and we will get 2 alpha chains, and the gamma will still remain, hemoglobin F. This implies that in the fetal or hepatic hemopoiesis, the predominant hemoglobin found in the fetal stage is hemoglobin F. So hemoglobin F is the most abundant hemoglobin in the fetal stage when it comes to the blood cell production. Now, as the fetus is growing and advancing, and the bone marrow is coming in, there is also going to be a switch of the fetal hemoglobin to hemoglobin A. So what actually happens is that, from along the line, the fetal hemoglobin, this gamma here will be switching, gamma hemoglobin will gradually be switching to the beta hemoglobin. The gamma hemoglobin will be switching to the beta hemoglobin. And the beta hemoglobin, once the gamma switches to beta, then we'll have 2 alpha chains, then 2 beta chains. And this is called hemoglobin A. And that is the aldol hemoglobin. There is also a switch of the gamma to delta. So there is also a switch of the gamma to delta. So if gamma switches to delta, then that means that we are going to have 2 alpha chains and 2 delta chains. And 2 alpha chains and then 2 delta chains will give rise to a hemoglobin we call hemoglobin A2. So these are the 2 main hemoglobins that are found in the aldol stage, and some percentage of hemoglobin what? F. So we are saying that in the embryonic hemoglobins which are found in embryonic hemoglobins, they are the GOA, the hemoglobin GOA1, hemoglobin GOA2, then we have hemoglobin Portland. So we have hemoglobin Portland. So these are the 3 major hemoglobins found in the embryonic stage, and this is made up of 2 zeta chains and 2 epsilon chains. This is made up of 2 alpha chains and 2 epsilon chains. This is made up of 2 zeta chains and 2 gamma chains. So this is the embryonic hemoglobins that we mentioned. And then when we comes to from the embryo, we now come to the fetal. And the fetal hemoglobin majorly is hemoglobin what? F. So this is the predominant hemoglobin. And as the fetus is aging, there is a switch. The fetal hemoglobin is made up of 2 alpha chains and 2 gamma chains. So there is also a switch of the gamma chains to beta chains, and there is a switch also of the gamma to delta. And so if it switches to alpha, it means that as the fetus is aging, or as the gestational age increases, then we'll begin to have another type of hemoglobin we call the aldol hemoglobin, which is called the hemoglobin A. So if this gamma switches to beta, so if the gamma switches to beta, if the gamma switches to beta, we'll have 2 alpha chains and then 2 beta chains. And this is what is called hemoglobin A. But if the gamma switches to delta, we'll have 2 alpha chains and then 2 delta chains. And this is what is called hemoglobin A2. And so since it is still in the fetal stage, certainly we'll have, so in the fetal stage we'll have hemoglobin F, we have hemoglobin A, and hemoglobin what? A2. So these are the major, but the predominant hemoglobin found in the fetal stage is hemoglobin F, and some amount of hemoglobin A, and a lesser amount of hemoglobin A2. So these are the fetal hemoglobin. Now, when we move from the fetal stage, the newborn, the baby has now moved from the womb, that is intrauterine, to the extrauterine. Intrauterine is talking about when the baby is in the womb, and extrauterine is when the baby is out, after delivery. So these hemoglobins that we have mentioned, the intrauterine hemoglobin, so this is intrauterine hemoglobin. Intrauterine. Intra means inside, uterine means uterus. The uterus is the womb. All these hemoglobins that we have mentioned, hemoglobin GOA1, hemoglobin GOA2, hemoglobin Portland, and in the fetal hemoglobin, they actually have a higher affinity for oxygen. they have a higher affinity for oxygen. And the reason why these hemoglobins have a higher affinity for oxygen is that in the intrauterine, there is less oxygen there. There is less oxygen in the uterine. In other words, there is hypoxia. So there is hypoxia in the uterine. Because of the hypoxia in the uterine, we need hemoglobin molecules that has a higher affinity for oxygen, that it can easily bind to the oxygen and will not easily give up the oxygen, so that the cells will have enough oxygen. So at the end of the day, because of the intrauterine hypoxia, and as a mechanism to get enough oxygen, the body or the hemoglobin type that will be produced in the embryonic stage, in the fetal stage, that is the period or the gestation, the period in which the baby is still in the mother's womb, we have to be producing hemoglobin molecules that have a higher affinity for oxygen. Now, when the child is now being given birth to, remember, in the third aspect, we will now have what we call the neonate. Neonate means new birth or newborn. In the newborn, remember that this newborn still have hemoglobin F, but the hemoglobin F is gradually switching to hemoglobin A. So by the time the child reaches from the third to the 6th month, almost all the hemoglobin F, the gamma globin chains have been switched to the beta globin chains and the delta globin chains, giving rise to hemoglobin A, hemoglobin A2, and the remaining hemoglobin F. So this becomes the most abundant hemoglobin in the newborn. The most abundant hemoglobin in the newborn after 3 to 6 months. So after 3 to 6 months, the most abundant hemoglobin is the hemoglobin A, hemoglobin A2, and then a lesser amount of what? Hemoglobin. So in order of levels, after the 6th month, when the baby is now outside the uterine, the most abundant hemoglobin becomes hemoglobin A, hemoglobin A2, and hemoglobin F. And these have a decrease. So here, this has a lesser affinity for oxygen as compared to this one and as compared to this one. This one has a higher affinity for oxygen. This implies that as the hemoglobin molecules undergoes a switch from the embryonic stage to the fetal stage, and from the fetal stage to the adult hemoglobin, there is a decrease in affinity as the switch of the hemoglobin molecules occurs. So there's a decrease in oxygen affinity up from the intrauterine up to the point that is the extrauterine, outside the womb, that is after birth. So that is it for the hemoglobins that are found after in the newborn within after the third to the 6th month. These are the predominant hemoglobin molecules that we see. So in adults, the most abundant hemoglobin in adults, or the hemoglobin molecules that are found in adults, include hemoglobin A, hemoglobin A2, and hemoglobin F. Likewise, the hemoglobin molecules that are found in the fetus include hemoglobin A, hemoglobin A2, and hemoglobin F. But that becomes the other way around, the reverse, when it comes to the most abundant. The most abundant hemoglobin in the fetal stage is F. Then we talk about hemoglobin A, and then we talk about hemoglobin what? A2. So simply these are the hemoglobin molecules that are found in the various stages or the various developmental stages with respect to the various organs and tissues that are involved in the production of blood cells. Let me quickly introduce this terminology with respect to blood cell production occurring inside the bone marrow and those that are occurring outside the bone marrow. Remember that the blood cells production occurred in the yolk sac, or it's also occurred in the liver, then the spleen. And blood cell production occurring inside the liver and the spleen comes with a terminology. And we have blood cell production in the bone marrow, specifically the red bone marrow. Blood cell production in the liver and in the spleen is outside the bone marrow, and anything outside is called extra. And blood cell production inside the bone marrow is called intra. So inside of the bone marrow, what is there? There is medulla. So the bone marrow, the inside of the bone marrow is called medullary. So in the medullary, what is happening there? There is blood cell production going in there. So the production of blood cells inside the bone marrow is called intramedullary hemopoiesis. Intramedullary hemopoiesis. Whilst the production of blood outside the bone marrow, that is outside the bone marrow, is called extramedullary. That is outside the medullary of the bone is called extramedullary hemopoiesis. Extramedullary hemopoiesis. So intramedullary hemopoiesis is also called medullary hemopoiesis. Medullary hemopoiesis. So basically, these are the terminologies we use. So at the point where we are talking about liver and spleen blood cell production, we are talking about the production of blood cells outside the bone marrow, and for that matter, that becomes extramedullary hematopoiesis. And the production of blood inside the bone marrow is called the intramedullary or the medullary hemopoiesis. In our subsequent lecture, we will look at the various stages or the individual production of the various cells.